All right, welcome to another video. So the last video I spent the whole time, it was about 13 minutes on the first explorational exercise. So really great video. Unfortunately, I had a technical issue. I unplugged my own cable and that caused the recording to stop. I think the recording stopped when I plug it back in. So it kind of stopped at a weird spot. I'm not sure. I don't remember exactly where it stopped. I actually have the video here. So, okay. So it looks like it stopped um, with this. Yes, you're on the right track. So the good thing about using this as a personal tutor is we got the whole conversation history here. So like I thought I fixed the issue by plugging the cable back in, but that's actually what uh, made it so that the video had to end. So all I need to do is do a review of this, and then I can move on to the next question. So um, this one's uploading in the meantime. So here we go. So uh, we'll start here. You're on the right track. UEFI uses an EFI system partition (ESP) where bootloaders for all installed operating systems reside. When you install a new OS on a UEFI-based system, the new bootloader is added to the ESP rather than overriding any existing bootloader. So it's appended to the ESP instead of overriding the MBR. This would happen with the MBR in the BIOS system. So in a BIOS system, you only have MBRs. You only have one MBR. If you install another OS system, you overwrite the MBR with the files required to boot the new operating system. If those files are not compatible with the other operating system you have, then you are unable to boot that other operating system since you only have one MBR. In a UEFI system, since the bootloader files are appended to the EFI system partition, you don't need to concern yourself with those compatible issues as you would on a BIOS system. So then it asked me, can you elaborate on how UEFI firmware chooses which bootloader to use when there are multiple operating systems? And this one I was able to answer correctly by answering the UEFI firmware chooses which bootloader to use when there are multiple operating systems through either user selection in the bootloader menu or through a configured default in the UEFI configuration utility. That's correct. The UEFI firmware maintains a list of valid boot entries in its NVRAM. The list is generated from the bootloaders in the ESP. The firmware can boot any of these entries, giving the user the option to use an operating system in a multi-boot setup. Additionally, the default boot entry can be changed via the UEFI setup utility. This system provides a more flexible and robust way to manage multiple operating systems as compared to the BIOS/MBR method, where the single MBR could be overwritten, potentially leaving other operating systems inaccessible. To summarize, why would overwriting the bootloader not happen on a machine equipped with a UEFI firmware when a new OS is installed? Overwriting the bootloader when a new OS is installed would not happen on a machine equipped with UEFI firmware because the bootloader files are contained within an EFI system partition, which allows files to be appended to the necessary folders instead of overwriting the existing bytes of the disk. Exactly, you've got it. In a UEFI system, each operating system's bootloader is stored independently within the ESP. Installing a new OS adds a new bootloader to the ESP rather than overwriting an existing one as in the BIOS/MBR system. This design allows multiple operating systems to coexist without interfering with each other's bootloaders. Well done on understanding this complex concept. So, yep, got it. The complexity lies within the understanding that the MBR can only exist one time, and if you install another operating system, the MBR is overwritten to contain bootloader files relevant to that operating system, and the bootloader files relevant to the other operating system that you have on there get overwritten. So the files in your MBR have to be compatible with both operating systems, which is often uh, tricky. With the UEFI, you can just have two sets of files, one for each of your operating systems you would like to run, or more than that. So, what is a common consequence of installing a custom kernel without providing an appropriate uh, init RAM FS image? So, I'm gonna move on to the next question here. Okay, so we'll say act as my LPIC-1 tutor, use the Radic method to teach me the answer to this question. And I will read the question. I already read it once, but I will read it twice. What is a common consequence of installing a custom kernel without providing an appropriate init RAM FS image? So let's think about what that well, let's just hit enter and have it teach.
Let's begin by breaking down the elements involved in the question. To start, do you know what an initial RAM file system is?
So I remember it a bit. My consistency in making these videos has been, to put it technically, dog S. And the S does not stand for super fun surprise. Well, it might fun and not well, anyway, let's move on from that. Hopefully, going forward, I can make videos every day. But the point is, I don't really remember what this is. I remember reading about it a bit, but I'm just not studying consistently enough to have a very clear memory of that, unfortunately. So let's go back and review it. And the first instance in this lesson is here. The kernel will open the initial RAM file system. The initial RAM file system is an archive containing a file used as a temporary root file system during the boot process. So let's enter that in there from memory. The initial RAM file system is a temporary archive containing and I don't remember, containing the initial files using during the boot process, containing, so let me, okay, I'll just copy this and type it again. So the init remfs initial RAM file system is an archive containing a file system used as a temporary root file system during the boot process.
That's correct. The initramp is indeed an initial root file system that's loaded into memory during the Linux boot process. Its main purpose is to prepare the real root file system by doing tasks like loading necessary drivers or setting up necessary devices. So, with that in mind, what would happen if the system doesn't have a suitable initramp when it attempts to boot?
Okay, so then I'll just answer on my own. It wouldn't be able to prepare the real root file system by doing tasks like loading necessary drivers or setting up necessary devices. Now I need to take a break here.
Right again. If the initramp is absent or not properly configured, it might fail to load necessary drivers or prepare other crucial parts of the system, including those needed for the proper operation of the real root file system. Now, let's think about what that means in the context of a custom kernel. If you compile and install a new kernel, what are some of the things that might be different compared to the kernel you are replacing?
Okay, good question. I'm going to pause and come back and answer. All right, so we can keep going for a few more minutes here. So ready again if it's not, yep. So now let's think about what it means in the context of a custom kernel. If you compile and install a new kernel, what are some things that might be different as compared to the kernel you are replacing? Uh, okay, well, I mean, let's go back and look at like what a kernel. So the main purpose of it is to provide the required modules so that the kernel can access the real root file system. As soon as the root file system is available, the kernel will mount all files. Um, Initialization. So this question, what are some things that might be different compared to the kernel you are replacing? So the new kernel might so what are some things that can be different from kernel to kernel? Um, hmm. So, in order to control the machine, the operating system's main component, the kernel, must be loaded by a program called a bootloader, which itself is loaded by a pre-installed firmware such as BIOS or UEFI. The bootloader can be customized to pass parameters to the kernel, such as which partition contains the root file system or in which mode the operating system should execute. Once loaded, the kernel continues the boot process, identifying and configuring the hardware. Um, so there could be different. Lastly, the kernel calls the utility responsible for starting and managing the system's services. So what are some things that might be different compared to the kernel you are replacing? The kernel might have different ability uh, with the hardware on the system, with the hardware with the hardware and system services on the system.
Exactly. The new kernel might have different hardware support or configurations. This could include different file system support, driver modules, or even different approaches to handling certain system services. And so, if your new kernel requires different modules or a different setup process than your old kernel, but you do not provide an updated initramps, what do you think might be the consequence?
Okay. Compatibility. The hardware. So if your kernel requires different modules or a different setup process than your old kernel, um, so let's think about what that does. The system. Um, oh, this is an explorational exercise. So, oh wait, no, I want to look. Yeah, I want to look at what's written about this. So, if you don't update the initial RAM file system, um, then it won't be accessed. The main purpose of the initial RAM file system is to provide the required modules so that the kernel can access the real root file system. So if you don't update that, so if you do not provide an updated initial RAM file system, then the kernel may not be able to access the real root file system of the operating system because it will not contain the required modules. You need to you need to update the initial RAM file system to ensure that the required modules are present.
Absolutely correct. If the new kernel and the initramps aren't compatible, it could lead to a variety of issues, such as an inability to boot the system. This is because the initramps might not contain the necessary drivers or modules required by the new kernel to properly access and use the real root file system. This is a common consequence of installing a custom kernel without providing an appropriate initramps image. In conclusion, it is crucial to ensure that when you compile and install a custom kernel, you also create an appropriate initramps image that matches the needs of your new kernel. Otherwise, you risk creating a system that cannot boot or function correctly. Would you like to learn about another topic or dive deeper into this one?
Okay, so perfect. We got that one done. Looks like the previous video is uploaded, so I can close this. So let's take a look at the answer for this. So the answer here is that the root file system may be inaccessible if its type was compiled as an external kernel module. Let's say, could this be the correct answer to the original question?
Absolutely, your understanding is spot on. If the root file system type was compiled as a module, the kernel itself doesn't have the ability to read that file system type. Hence, if the initramps is missing or doesn't have the required module to read the root file system, the kernel won't be able to mount the root file system, making it inaccessible. So, you're correct. A common consequence of installing a custom kernel without providing an appropriate initramps image is that the root file system may be inaccessible if its type was compiled as an external kernel module. This could ultimately prevent the system from booting up successfully. Keep in mind that while this is a common scenario, it is one of several potential issues that could occur when dealing with custom kernels and initramps. Different configurations may lead to different problems.
What is an external kernel module?
An external kernel module, also known as a loadable kernel module, is a piece of code that can be loaded and unloaded into the kernel on demand. They extend the functionality of the kernel without the need to reboot the system. For example, drivers for many types of hardware are provided as loadable kernel modules. These modules can be loaded when a particular piece of hardware is in use and then unloaded when it is no longer needed. If a file system type was compiled as an external kernel module, it means the kernel itself doesn't have the built-in ability to interact with that file system. Instead, it relies on this external module to provide the capability. Does that help to clarify what an external kernel module is?
Okay, this is the only time I kind of don't like it when this happens, when they introduce like a new concept like that as part of like a check your understanding question. But an external module, also known as a loadable kernel module, is a piece of code that can be loaded and unloaded into the kernel on demand. So, for example, like a driver, like a kernel module, like a kernel module is an external kernel module. An external kernel module is a kernel module. All right. Act as my LPIC-1 tutor. Use the Socratic method to teach me answer to this question. All right, question is, the initialization log is hundreds of lines long. So the output of DMESG of the command is often piped to a pager command, like command less, to facilitate the reading. What DMESG option will automatically paginate its output, eliminating the use to use a pager command explicitly?
The Socratic method is a form of dialogue, so let's begin. Are you aware of the basic structure of the DMESG command and how it displays the kernel ring buffer? Once we've established that, can you tell me what you understand about command line options, how they modify the behavior of a command? Next, if you have a command and you want to see what options are available, what would you typically do? Finally, given what you've shared, could you make an educated guess as to which DMESG option might automatically paginate its output, so you don't have to pipe it into less or another pager?
It's doing it differently. It's doing it in a way I don't like as much. It's just flooding me with questions instead of waiting for me to answer each one. Um, I'm going to take a break. I'll be right back. All right, I'm back. Feeling good. So, this kind of stuff is going to be annoying if it's on the test. Like, I don't remember what specific option. Like, memorizing options is dumb. Like, just do dash dash help. Like, memorize it. Like, if the test means you have to memorize options, then I don't like that. I think it's DMSG or DMESG message. Yeah, yeah, that's it. So I think it's this. Yeah, automatically. Yeah, so dash dash human is the answer. Yep. Okay. Well, next one. All right. So let's move on to the next one. That one was easy. And I'll use the same prompt I used for this one. Oh, wow, that is the same prompt. Okay. Okay. So next question. A hard drive containing the entire file system of an offline machine was removed and attached to a working machine as a secondary drive, assuming its mount point is dash MNT. Sorry, I mean forward slash MNT forward slash HD. How would journal CTL be used to inspect the contents of the journal file located at that path?
Certainly. Let's start with the basics. Journal CTL is a utility for querying and displaying logs from the system journal, correct? Can you tell me how you would use journal CTL to inspect the contents of the journal files located in the default location on a running machine?
Yes. So it would just be journal CTL, and then I don't think you need to feed it a switch. You just like that, right?
I see you're on the right path, but there seems to be a minor confusion in the command syntax. The default command to view the logs using journal CTL is just journal CTL without specifying a path. It automatically reads from the system's default log location, which is var log journal. However, in the scenario you've outlined, you're dealing with a secondary hard drive with a mount point of MNT HD. Given this, can you think of the steps you might take to direct journal CTL to read logs from the secondary drive?
Oh, did I enter it in wrong? Oh, yeah, I made a typo. I did mlog instead of that. So yeah, okay. Let me type in the correct answer. There we go.
Close, but not quite there. The journal
Uh,
CTL command doesn't directly accept a path argument like that. Instead, it checks the system_journal environment variable to determine where to look for journal files. So, in this case, how might you change the system_journal variable to point journal CTL to the correct directory?
oh, that's weird. Is it because I messed this up? So you can do systemd journal equals hd var log.
That's the right idea, but there's a small mistake in the variable name. It should be system_journal_path, not system_journal. Once you've set the environment variable correctly, the command journal CTL will read from the directory specified in system_journal_path. Do you think you can correct your command now?
Okay, I think it's hallucinating. I think me doing that typo by accident really messed it up. I think let's see
Yes, that's
here.
correct.
Yeah.
Now, to make journal CTL use this environment variable in the current session, you'd use the export command. Can you try writing the full command that sets the environment variable and then calls journal CTL?
Yeah. And then calls it. Uh, oh, not echo.
You're almost there. We need to use export instead of echo in this context. The echo command is used to display a line of text or string on the standard output or into a file. On the other hand, export is used to set environment variables in Linux. Can you try again using export to set the system_journal_path environment variable? Then run journal CTL to view the logs. Excellent. That's the correct sequence. First, you're setting the system_journal_path environment variable to point to the appropriate directory on the secondary drive. Then, you're running journal CTL to inspect the logs stored in that location. Remember that the export command only sets the environment variable for the current session. If you want to make this change permanent, you would have to add the export line to a startup file like tilde. Bash or tilde. Bash_profile. Does this clarify how to use journal CTL with a secondary hard drive's journal files?
Okay, so got off on a little bit of a tangent there. So the question was a hard drive containing the entire file system of an offline machine was removed and attached to a working machine as a secondary drive, assuming its mount point is /mnt/hd. How would CTL journal be used to inspect the contents of the journal files located there? So this is a pretty easy one. You just do journal CTL. You don't need to add a switch or anything. Then you give it a path to where to inspect the contents of the journal files. Uh, Automatically, if you just provide it, it uses a default path. The default path is /var/log/journal. ChatGPT took me on a bit of a journey, a tangent to change that default path, but that's overcomplicating the question. The answer is as simple as journal/mnt/hd, and then here. So yep, really easy question, really easy answer. So next is a summary. This lesson covers the boot sequence in a standard Linux system. Proper knowledge of how the boot process of a Linux system works helps prevent errors that can make the system inaccessible. The lesson goes through the following topic areas: how BIOS and UEFI boot methods differ, typical system initialization stages, recovering boot messages. The commands and procedures addressed were common kernel parameters, commands to read boot messages, which are dmessage and journal CTL. So let's see what the answer was to that. Oh, shoot. No, you do need a switch. You need to do -D. Okay, well, I got that wrong. Um, Let me enter this in there.
Indeed, you got it. Using the D option, or directory, is an alternative and direct way to specify the journal directory path for the journal ctl command. So, your full command becomes: this will tell journal ctl to inspect the logs located at mnt hd var log journal. Great work in reaching the answer. Do you have any other questions or scenarios you want to discuss?
All right, so that's it for this section 101.3. Stay tuned for the next 101.2. Stay tuned for the next section, which will be 101.3. Thanks for watching.